Are we ready? All right, so if you guys loved radicals. Okay, wait, you guys. What if I told you there was a way to combine our love of radicals and vectors and put them all in one chapter? Huh? Yeah, it's so great. Okay. So, a quick bit of notation. In most math books, we use I to represent the square root of -1, but this is not just any math book that we're using. It's a technical mathematics book used by engineering majors mostly. So in the field of electrical engineering, little I is used to represent a variable current, and so that's why we use J to represent the square root of -1 instead of little I. It is, if you like I's instead of J's, feel free to use I's. That's fine. Just be consistent. Don't mix I's and J's together because that makes no sense at all. So all we do is we take our set of real numbers, like the real number line that we know and love, and we're going to add something to it. Now, the number itself is not real. Sydney, Cassidy, are you just having a hard time containing your excitement?
Yes.
Okay. We add a number to the real numbers. I mean, this number itself is not it's not that this is a real number, but we're going to add something to this to create a whole other set of numbers. And that is J. It's a square root of -1. It is the number such that when you square it, you get -1. And really, this number came about by somebody saying, looking at when we solve quadratics or when we solve polynomials in general, right? And we said, well, x squared minus 1 equals 0. Like, we know how to solve that. We could factor it. And we get x equals -1 or x equals 1. All kinds of equations that we solve. And then for the longest time, we looked at an equation like this, x squared plus 1 is equal to 0. And we're like, well, it just doesn't have a solution. And the thing is, it does not have a solution in the real numbers. But somebody was like, dude, it's got to have some kind of solution somewhere. So they said, let's subtract 1 from both sides. So we get x squared equals -1. Clearly, the value of x, there's no real number you're going to square and get -1. So they're like, okay, I know this thing is not in our set of real numbers, but I'll just consider its solution. So if I take the square root on both sides, I get x is plus or minus the square root of -1. It has two solutions. They're just not real numbers. So this new number that is not a real number, right, so it's something new, we just decide to call it J. And it is the number such that if you square it, you get -1. And then we see where that gets us. So we're going to begin by just working with this expression, this new number J, seeing it as the square root of -1, and working with radicals. Right? So just coming off the heels of what we did, this is very similar to what we've been working on. The difference is, if I want a square root of a negative, if there's a negative in here, the first thing I do, if there's a negative in here, I pull that out as a J. So this is J times the square root of 9, or 3J. The square root of -1/4, again, here I've got this negative, so I could pull that out as a J. What is the square root of 1/4? What do I square to get 1/4? 1/2, yeah. So this is 1/2 J. And this one, here's a negative, so we pull this out as a J. And we just get J root 5. 5's not a perfect square or anything. It's already simplified as a radical, so I just leave it as J root 5. Now you'll notice sometimes I put the J at the end and sometimes I put it in the front. Usually whenever I have any coefficient or factor in front with a radical, I write it in front so it doesn't look like it's inside the radical, so that's why I write it out front here. It is, if you wanted to call this J3 instead of 3J, go for it. Lots of people do it. Okay. So we have to be a little bit careful with the rules of radicals. We've always had to be careful with the rules of radicals, but one of the rules of radicals that we use a lot are that the square root of a times the square root of b is the square root of a times b. Now that's true. That equation is always true as long as a and b are not both negative. All right? So if one is negative and one's positive, or if they're both positive, that always works. If they're both negative, we have to be super careful. So if we're dealing with square roots of negatives, we always want to pull out that j first. So let's work through some examples. Here we are squaring a square root. So we think, well, I know that when we square something, that means we multiply it by itself. And now, instead of combining this radical and calling this the square root of positive 16, right, because negative 4 times negative 4 is positive 16, what I got to do is deal with these guys first. So I pull out a j. So I got j root 4 times j root 4. And I guess I'm doing this slightly the long way, but root 4 is obviously 2. So I've got 2 times 2, which is 4, and then j times j, which is j squared. What's j squared equal to? Yeah. So overall we get negative 4. Now who here is relieved that when I took the square root of negative 4 and squared it, I in fact did get negative 4. Whew. That's a good sign, right? So there's me doing something out kind of the long way, but just sort of showing that this technique, we have to be careful right at this first step here. If I write that as the square root of negative 4 times the square root of negative 4, we've got to make sure we pull those j's out first before we combine as a radical. Let's do another one. So what do we do first here? Take out the j's. So these j's come out. So I got j rad 3 times j rad 12. And now these are regular old radicals, right? Like from the last chapter. So 12 12 is 2 times 2 times 3. And in fact, actually, if you guys don't mind, and this might annoy you, and I am kind of sorry, but I'm gonna do this slightly more efficiently. Okay, so I've got a couple of j's here, right? That's a j squared. And then inside, now that these guys here are both positive 3 and positive 3, positive 12, now I can combine them and call it the square root of 36. Oops. What's the square root of 36? Yeah. And what's j squared? Yeah. We get negative 6. You would eventually get the same thing, right, if we worked it out and factored them all, but the numbers were convenient enough that I figured it was a little bit more efficient to do it this way. So we get negative 6. Let's compare that to this one. Inside, I've got the product already sitting inside the radical. So I have to multiply first. This is an order of operations things. I'm not multiplying two radicals, each of which has a negative inside. What I've got is a radical over the whole product, which means I've got grouping symbols. Order of operations tells me here I've actually got to do that product first. So this is the square root of 36, and we just get 6. And the thing to notice here These are not equal. Right? In other words, root negative 3 times root negative 12 is not the same as root negative 3 times negative 12. That's what that little note of caution means at the top of this page. That property that says, oh, we can combine radicals under multiplication holds as long as both factors, as long as they're not both negative. It holds. But as soon as they're both negative, like, we've got to deal with those j's first. Want to do another one?
Yes.
Yes. Yes. Okay. What do we do first?
Make the value of the radical positive. Or take out a j.
Yeah, yep. So we take out a j, which takes care of that negative inside. So outside we have minus j, because we still have that negative outside the radical, root 75. And 75, make a little factor tree for this, 3 times 25, which is 5 times 5. We got a pair of 5s we can take out. So we have minus 5j root 3. More? I keep asking like as though it's our choice, and I know like maybe that gets annoying, but more! There, now it's not a choice, now it's not a question. Alright, so let's compute some powers of j. J to the first, just like anything to the first power, is itself, right? So j to the first, that's just j. What's j squared? Negative 1. So that's our new definition, right? New fact for today. J squared is negative 1. Now j cubed we could write as j squared times j, just by rules of exponents, right? Plain old rules of exponents. So what should this give us? What's j squared? Negative 1 times j, or negative j. J cubed is negative j. That's kind of interesting, don't you think? Can you think of other numbers where that happens, where you cube something and you just get the negative of the number? I can't. J to the fourth, so one way we could think of j to the fourth is j squared times j squared.
Negative 1 times negative 1.
Uh-huh.
So 1.
Yeah. So, okay, j to the fourth is equal to 1. Before we keep going with the rest of these, I just want to take a moment and observe that the equation x to the fourth x to the fourth equals 1. We used to think, right up until now, if we were to solve this equation, we'd say, oh, 1 or negative 1, right? Like, what number do I raise to the fourth power and I get 1? Well, 1 to the fourth is 1, and negative 1 to an even power, right? That'll be positive 1. Looks like j is also a solution. So there's a third solution to that equation. J to the fifth. Let's see.
So that's 2j cubed, or squared.
Yeah, yep. Or I see where you're going with that. So I think maybe a slightly more efficient way is j to the fourth times j. Because what's j to the fourth equal to?
Negative, just 1.
1, positive 1, right. So a factor of j to the fourth is like a factor of 1. It's like it's not even there. So what's j to the fifth equal to? J. All right. Now j to the sixth, let's do the same way we did j to the fifth. Let's start by taking that j to the fourth out. So j to the fourth times, and then what's left?
J squared.
J squared, right? Just rules of exponents. So what is this going to give me?
A negative 1.
A negative 1. Okay. All right. So we get j to the first is j. J squared is negative 1. J cubed is negative j. j to the fourth is 1. Then j to the fifth is j. Then j to the sixth is negative j. Now, without doing anything, without like doing out the algebra, what do we think j to the seventh is going to be? Negative j. What about j to the eighth? What about j to the ninth? J. What about j to the 10th? Yeah, how do you get that? It's a pattern, yeah. So we have really just, this is our pattern. We take j, we keep raising it to higher and higher powers, and we just get the same 4 values repeating. Name a time that happens with real numbers. I don't think you can. I mean, aside from 1, right? If you take 1 and raise it to different powers, or negative 1 and raise it to different powers. Now we have another value where that happens. So this pattern seems to be 4 values long, right? 4 distinct values that we get when we just take j and raise it to different powers. And if we raise j to a power that is a multiple of 4, we get 1. I'm taking a moment, I'm going to actually put it in the notes here because this is actually important. For example, we kind of just found j to the 8th, we just kind of kept the pattern going, right? But if I wanted to find j to the 20th, for example, well, I would say, since that's a multiple of 4, and this fact tells me that I should just get 1, but we can convince ourselves of that. This is 20 is 4 times j. The fact that it's a multiple of 4 seems to be important the way this fact is worded. So I'm going to write it as 4 times 5. And multiplying exponents means we were raising to a power, like a power to a power here. J to the 4th is 1, and 1 to the 5th is 1. So here's sort of an illustration of why if I raise j to a power that's a multiple of 4, we just get 1. You can always use just the rules of exponents, right, and write this out as now a power. If this exponent's a multiple of 4, that means that j to the 20th is a power of j to the 4th, which means it's a power, it's just 1 raised to some power. So we can use this pattern to our advantage to make some powers of j, to make computing really any power of j trivial. So the first thing we do is we try to take out those multiples of 4. So 10 is not a multiple of 4, right? But what I can do is write this as 4 times 2 plus, right, because 4 goes in there twice with 2 left over. Watch this. Here we're adding in the exponent. What does that correspond to? Multiply. So this is j to the 4 times 2 times j squared. This j to the 4 times 2 is j to the 4th squared. Now what is the j to the 4th squared equal to? 1, right? Because it's 1 squared. So that's just 1, which means all we're left with is j squared. And of course j squared is negative 1. So what's important here is that we rewrote that exponent 10 as, taking out whatever multiples of 4 were left and then finding whatever remained, right? So another way to think of this expression here when we rewrote 10 is that I'm thinking of 10 as some multiple of 4 plus a remainder, right? 4 goes in however many times. I almost don't care however many times because 2 is what's left over, and that is the only thing that remained here. So if we could really just figure out what this remainder is when we divide by, when we say that 10 is 4 times 2 plus 2, the important part of that is saying that 10 has a remainder of 2 and we divide it by 4. So if I want to figure out what j raised to the 531 power is, I'm going to take 531, I'm going to divide it by 4. 4 goes into 5 once. 4 goes into 13 3 times. 12. 4 goes into 11 twice. So then that's 8 with 3 left over. So the upshot of this is that j to the 531 is equal to j cubed. We could show it out using like kind of the algebra with the exponents the way we did before, but it'll just be j cubed, and we've already seen that from the top of the page that this is equal to negative j. So if I wanted to use this to show using the rules of exponents, we'd say, well, j to the 531 is equal to j to the 4 times 132 plus 3, and this is j to the 4 to the 132 times j cubed, and j to the 4th we know is equal to 1. But the big, the important part of this was just, what is the remainder? When I take that exponent, divide it by 4, what's the remainder? And that's the only thing that's left. When we just cycle through. When we raise j to a power, like whatever power, that says how many times through the cycle, right? Like how many steps. We know that this cycle is just 4 steps long. Every time I raise it to the 4th power, that's just 1 time through the cycle. We have so far been working with numbers that are purely imaginary, meaning they're just j or some multiple of j, some real number multiple of j. But a complex number really is any number of the form a plus b times j, where a and b are real numbers. So the number a that appears that doesn't have the j, we call that the real part. And b, like b itself is a real number, but whatever that coefficient on j is, we call that the imaginary part. So let's say I have a couple of numbers, couple of complex numbers, a plus bj and x plus yj. They're equal precisely when both their real parts are equal and their imaginary parts have to be equal. I mean, I think if we were to figure out or define what we think should be true for two complex numbers in rectangular form to be equal, we'd probably say the same thing. They have to have the same real parts. They have to have the same imaginary parts. Everything has to match up exactly. So that's what this fact says, right? So if their real parts are the same, a is equal to x, and their imaginary parts are the same. So we can use this fact to solve some equations here. If a plus bj is equal to 3 minus 4j, well, this is really just a direct application of this fact. If these are equal, then the real parts have to be equal. We must have a equal to 3. And if these numbers are equal, then their imaginary parts must be equal. And so we must have b equal to negative 4. Note that I'm grabbing that sign as well. We can also solve some equations that are not quite so simple. But using the same premise, like two complex numbers are the same if their real parts are the same and their imaginary parts are the same. So here, let's say, so here the imaginary part is a minus 6j. I'm just going to rewrite these numbers. So I'm going to have 4 minus x, so I can write the real part at the beginning, and then minus, and I'll write that as plus, negative 6j. All I've done is regroup the terms on the left side, so I put the reals in front, and then the imaginary part is at the end. On the right side, it's all imaginary, right? So I've got the real part is 0. And what is the imaginary part? Say that again?
1 plus 1?
Yeah, 1 plus y. It's sort of like saying, oh, I'll just factor that j out to get the imaginary part, right? Whatever, this is some multiple of j, I'll just factor the j out. So now we've sort of written each of these explicitly, and it's like rectangular form, like real part and imaginary, real part and imaginary part, real part and imaginary part. So now we can use that fact above. If these are equal to each other, the only way this happens is if the real parts are equal and the imaginary parts are equal. Oops. And now we can just solve each of these without too much. They're just linear equations, right? So in the red equation here, for the real parts, we get x equals 4. And solving for y, we get y equals -7. How fun is that?
Super fun.
Super fun. All right. So on the next page, we define the conjugate of the number. Now this, I hope, will not come as much of a surprise. J is defined to be the square root of -1. We've already seen the term conjugate come up in when we were working with radical expressions. If I wanted to, here we go. If I wanted to rationalize, this is going to have nothing complex in it. 2 plus root 3. If I wanted to rationalize the denominator, what would we multiply by? Nope. 2 minus root 3, and we had a name for that. This 2 minus root 3 is called the conjugate of this, right? What we get when we just change that from a plus to a minus. So conjugate really means the same thing. We say that when we talk about the conjugate of a complex number, or we call it the complex conjugate, we specifically mean we are changing the sign of the imaginary part. And which should make sense, right? Like the conjugate of, 2 plus j or something, right? This is the conjugate of 2 plus the square root of -1. Of course, it should mean that we're changing that. The j is where the radical is, right? So we're doing the same thing that we did to get that value that we were using to rationalize. So to get the complex conjugate, just change the sign of the imaginary part. So the conjugate of 3 minus 2j is? Yeah. And the conjugate of -2 plus 5j?
-2 minus 5j.
Mm-hmm. And the conjugate of 6j? -6j. And the conjugate of 3? 3. Right? The imaginary part is 0. I want to give like a geometric interpretation of these conjugates. So we're going to do a lot more of this particular type of thing or we're going to think of complex numbers in this way a whole lot. But the real numbers, we're used to all real numbers fitting on a line, right? They're one-dimensional. The real number line. Complex numbers, every complex number has a spot in the plane. They're two-dimensional. So the first thing we do is we have our this is our regular old real number line. Horizontal, right? Those are the reals that we know and love forever and ever. Then we take our imaginary axis, perpendicular. We draw an imaginary axis perpendicular to the real axis. So if I want, so here's, my numbers 1, 2, 3, 4, 5, -1. And then on the vertical axis, on the imaginary axis, what I have is j, 2j, 3j, 5j, 6j, and then -j, -2j, -3j, and so on. Every complex number has a spot on the plane. So 3 plus 2j, that's 3 on the real axis, up 2 on the imaginary axis. There's 3 plus 2j. Its conjugate is 3 minus 2j, which is down here. It seems like to get its conjugate, if we're just changing the sign of the imaginary part, all we're doing is sort of flipping this down, kind of reflecting it over across the real axis. -2 plus 5j, that's up here, right? -2 on the real axis, up 5j on the imaginary axis. So its conjugate is -2 minus 5j. Again, its conjugate just means sort of flip it over, reflect it across the real axis. Positive 6j, well, that sits right up here, right on the imaginary axis. Its conjugate, if we flip this over the real axis, is down here at -6j. Not surprising. And positive 3, well, that's right here. And if we reflect that across the real axis, since it's on the real axis, it doesn't go anywhere. It is its own complex conjugate.